So, oscillations. What are oscillations? Oscillations are literally what is happening to the word oscillations on the screen. Okay, ذبذبات, تموجات, vibrations, slinkies. Oscillatory motion is something that is periodic in time and repeating itself. So something like a pendulum, something like you might have seen on your grandfather's clock. Okay, I know it's 2021 and it's a new age and digital, and most of you, probably don't own, normal clocks anymore. Everything's digital. But you have seen this, I hope, at one point in your life, at least in your grandparents' home, maybe, where you have this huge clock with this long rod with a brass plate at the end, which goes left, right, left, right. Okay, we call it a pendulum. Okay, and what is special about this motion is that it is repeating. It keeps going from the same position to some other position and back to its initial position over and over again. It's repeating and it's periodic in time. It takes the exact same amount of time to go and come back over and over again. What are some examples of oscillations? One example is me talking to you right now and you hearing it. What happens is the vocal cords in my throat are vibrating. The air molecules around it vibrate at the exact same vibration. It oscillates. It keeps going on from one molecule to the next, to the next, to the next, until it reaches your ear. And then your eardrum takes those oscillations and translates them back into sound. You also have light rays. Light rays also oscillate. But the question is, what oscillates in light rays? Okay, in sound, we have air molecules, but light rays actually come all the way from outer space. So what oscillates in light rays? Turns out the answer is, if this is the direction of my light ray, if you move ahead in your book, you will see something that looks like this. You will see a drawing that looks like this. And what this is the electric field and the magnetic field. Now, we're not going to go into details of, what are electric fields and magnetic fields in this lecture or in this course even, but an indication of what's to come in future courses if you continue to take physics, which is very, very interesting, is that you have these electric fields and magnetic fields that oscillate even in vacuum, in outer space. Musical instruments. Anyone here plays guitar, violin, oud? You would know that you are strumming these strings to make different noises. If you hold it from here, you'll get a different note. You hold it from here, you will get a different note. You hold it from here, you get an even different note, and so on and so forth. Even atoms and molecules and subatomic particles are oscillating all the time. Okay, as a matter of fact, and again, we'll not go into details here, in advanced physics, you find out something called 0-point energy, which means that even when we go to minus 273.15 degrees Celsius or 0 Kelvin, even then you have this minimum sort of oscillation, vibration of subatomic particles at 0-point energy. But let's take the most simple of examples, the simple pendulum. it goes from a maximum position to another maximum position, through a minimum position in the middle, back and forth, right, left, right, left, left, right, left, right. Okay. And if we follow this motion in stop motion fashion, we will find that it takes half the amount of time, t, to go from maximum position to the other maximum position, and then exactly the other half of time going back to the initial maximum position. And we call the time it takes to go from point A to point B and back to point A, so a round trip, we call it t, time period. Now, where have we heard this before? We have spoken about time periods before. We have mentioned them before. Do you remember where we did that? We mentioned it in circular motion. Okay, in circular motion, we had this concept of time period, which is the time it takes to go one circle. And turns out it's not only a similarity in name, it is actually the same thing. So we have the time period, the time to go for one oscillation for one circle, and we also have the frequency, okay, which is the number of oscillations or the number of rounds per second. Okay. The unit of frequency is hertz, otherwise known as 1/second. We have seen this also before. We have done a lab on it, where you put a mass on a spring and the spring keeps going up and down. And what happens is, if you track the centerpiece, it goes through this maximum and minimum, and it keeps going back and forth between them. And if I actually try to track that in time, I end up with something that looks like a sine wave. And we call that sinusoidal motion. So what if I want to write an equation describing this movement in time? Well, it looks like a sine wave, so we probably should use a sine function there somehow, or a cosine function. But we need a bit more information to be able to describe it. First of all, sine and cosine functions go from -1 to +1. And well, these things can go more than 1. So we need to multiply it by something to be able to go to describe it properly. And that thing is what we call the amplitude, the maximum or minimum vertical distance between the graph and the x-axis. We also have the period, the time it takes to go from point A to B and back to point A, a round trip. We have a sine and a cosine function. And the way we write this equation is x of t equals a sine omega t. Okay. What is a? What is omega? Well, omega is what we call the angular frequency, and it is given by 2 pi f, or 2 pi over t. So we can describe it using either a sine or a cosine, depending on the situation. Now, if the motion is a sinusoidal function of time, we call it a simple harmonic motion, and it can be expressed in this form. I'll keep it on the screen, just copy it on a, because we're going to be using it in a bit. Sorry, just a second. I'll be back in a minute. Okay, sorry, I got disconnected. Okay, so I hope everyone copied this equation on a piece of paper because we're going to be using it. Mathematically, a simple harmonic motion, which is motion that is a sinusoidal function of time, can be expressed as x sine omega t plus phi or x cosine omega t plus phi. What is this? Xm is amplitude, the maximum displacement. T is simply time. Omega is angular frequency, which we already said is 2 pi over t. And phi is what we call a phase constant or a phase angle. What is a phase angle or phase constant? We'll describe that in a minute. But first, let's say we have two functions, two simple harmonic motions, which have the same period but different amplitudes. What would that look like? It would look like this. Exactly the same function, exactly the same time, but one of them goes higher or lower than the other because the amplitude is different. The maximum amount is different. So far, so good? Okay, what if we have same amplitude but different periods? What would that look like? We would end up with something like this, where the maximum and minimum are the same, but the amount of time it takes to go back from max to minimum to max is less. So here, our blue line has a time period t, and our red line has a time period half t, or t over 2, because it takes half the amount of time to start at the top, come back down, and all the way back to the top again. Okay, we have one more option. Same period, same amplitude, but different phase constant. And this is what we find. Now, a phase constant works very much like the constant c in integration. When we integrate, usually, say for example, integral of x dx, what is the answer? If I don't have limits, my answer is going to be x squared over 2 plus c. And then to find out what the c is, I need to put initial or boundary conditions. Okay. And the phase constant here is very similar to that. So this is a sine function. Okay. Now, at the moment, I actually have two sine functions here, only you can't see them because it's right on top of one another. I will start increasing the phase constant. I will first just put 0.1. And I'll increase it to 0.2. 0.3. 0.4. 1. What can you see? We have the exact same function with the exact same time period, with the exact same frequency, with the exact same amplitude. Everything is the same, but it seems like someone is pushing it in a direction to the left or to the right. Okay, and this is what we call a phase constant. It is literally a constant difference between two identical functions.
Victor, we cannot see the other screen. Only we can see the PowerPoint.
You should have told me this before. 1 second. Can you see my screen now?
Yes.
Okay. So this is the sine function I was talking about. And there are actually two of them here now. Only you cannot see them. They're exactly on top of one another. Now, if I start increasing, so at the moment, what I have is a sine omega t plus phi and a sine omega t, just omega t, let's keep it at that. Okay. Now let me, when phi is equal to 0, these two equations are exactly the same, a sine omega t. But once I start phi off with a number, look what happens. It's like someone is pushing the same function to a side. Yeah, and this is what a phase constant is. Same function, just off by a bit. Okay, so we call this a phase function, a phase shift or a phase constant or phase angle. Okay, if you're into electricity or electrical engineering and you're interested in that kind of thing, you would know that the electricity we have at home is called single phase, And the electricity that we have in industry, for example, is called three-phase electricity. So what happens is, at home, we only have one. Yeah. At home, we only have one electric connection, one voltage or one current in our wires that are actually working like this. But then in industry, to get more power in the same cables, without changing the cables again, we actually end up having this. End up with this, with three different lines in the same wire. So we get more power in the same wire. Okay, I have a question for you. What happens if the phase shift between the two lines is exactly pi over 2? This is what happens. My sine function becomes a cosine function, or my cosine function becomes a sine function, because the difference between a sine and a cosine function is exactly pi over 2, 90 degrees. Okay. If my position is x cosine omega t plus phi, how do I find velocity? I differentiate. And if I differentiate this, I end up with minus omega x sine omega t plus phi, because x is a constant. The derivative of cosine is minus sine, and using the chain rule, the derivative of omega t plus phi is simply omega. And since we have cosine and sine, then the shift velocity, the phase shift is pi over 2. If I want acceleration, I do this again, and I end up with minus omega squared xm cosine omega t plus phi, which is just x. So minus omega squared x over t. So my displacement and my acceleration are the exact same function, same time period, but they are in opposite directions. So it's flipped in the y-axis, sorry, in the x-axis. When x of t is positive maximum, acceleration is also maximum, but in the negative direction. When x of t is at the negative maximum, a of t is also maximum, but in the opposite direction, so positive. Any questions so far? Okay. Force laws. From Newton's second law, we know F equals ma, and we just derived a to be minus omega squared x. So we have F equals minus m omega squared x. And I can call m omega squared a different letter. I'll just give it the name k. So SHM is the motion executed by a system subject to a force that is proportional to the displacement of the system but opposite in its sign. And we have done this before. You have done it in labs, we have done it in other chapters. F equals minus kx springs. K equals m omega squared. So for a spring mass system, a spring constant k is related to the angular frequency omega of the oscillator by. You have ma on one side, which is equal to m omega squared on the other side, which is equal to minus kx. The x's go away, the minuses go away. I have k equals m omega squared, which means omega is equal to square root of k over m. Since omega is equal to 2 pi over t, t is equal to 2 pi square root m over k. So if we know the mass of a system and the spring constant, we can tell exactly how long will it take to oscillate between one point to another. Let's do a sample problem. If we have a block of mass 680 grams attached to a spring where the constant is 65 newtons per meter, the block is pulled a distance 11 centimeters from its equilibrium position at x equals 0. There's no friction, and we release it at t equals 0. We want to calculate the angular frequency, normal frequency, period, amplitude, maximum speed, position when it has this maximum speed, magnitude of maximum acceleration, phase constant, displacement function. We can do all of these by just knowing the mass, the spring constant, and the distance pulled. Okay. It looks impossible. How can we know so much information from only this? But let's do it. If we want to know the angular velocity, omega is equal to square root k over m. We know k, we know m. We have 9.8 radians per second. We want frequency, we just divide that by 2 pi. We get 1.6 hertz. So the system would go and come back 1.6 times every second. We want the time period, 1 over that. So 0.64 seconds or 640 milliseconds is the time the system takes to go and come back. If I want the maximum velocity, if we have a maximum velocity, how do you guys have final at the time of a lecture? What course is this? Okay, just give me the course code, please, and then you can go to your final. Good luck. Just type the course code and then good luck. Go to your final. The recording of this lecture will be on YouTube. You can take a look at it later. Okay. The maximum velocity, we said, is omega xm. We know omega. We know our maximum amplitude is 11 centimeters. We can get the maximum velocity. Same way, we can also get the maximum acceleration. And at the very end, we want now to find the phase constant and the entire displacement function. Okay. X of t, we said, is x cosine omega t plus phi. At time equals 0, okay, at time equals 0, it is released at x equals 0. We have 0 equals xm cosine omega t plus phi. We take the inverse of that, we end up with phi equals 0. Now the angular displacement needs to always be in radians. Okay, we cannot have an angular displacement which is in degrees. Okay, all the calculations need to be in radians. My final equation, xm cosine omega t plus phi, we substitute what is xm cosine. We have calculated omega before, so we write it there. T plus phi, we calculated phi to be 0, so it's 0.11 cosine 9.8 t. So it's amazing how much information. Now, of course, once I have x of t, I can find v of t and a of t. Yeah. Actually, I will write it down. V of t is going to be minus 0.11 times 9.8 sine 9.8 t, and acceleration is going to be minus 0.11 times 9.8 squared cosine 9.8 t. It is amazing just by knowing m, k, and maximum amplitude, how much information, how we could describe the entire system by simply knowing 3 very basic items. So you have done this in a lab before, and we looked at it when we're looking at conservation of energy. I showed you a simple pendulum, and I showed you a spring. Yeah, we said, look, there's potential energy, there's kinetic energy, there's gravitational, there's elastic, and they are being sheared left and right. Yeah. So the potential energy of a linear oscillator is associated entirely with the spring if the spring is horizontal. Okay, if it's vertical, then we also have gravitational potential energy, but for the time being, to keep it simple, I'll have it horizontal. So my potential energy is half kx squared, which is half kxm squared cosine squared omega t plus phi. And the kinetic energy of the system, again, since it is horizontal, is entirely associated with the speed of the block, so simply half mv squared. So my total energy will be u of t plus k of t, and it will be constant. And what's happening is the energy is oscillating between potential and kinetic. Less potential, more kinetic, more potential, less kinetic. The total mechanical energy of the system is u plus k. So half kxm squared cosine squared omega t plus phi plus half kx squared sine squared omega t plus phi. What is cosine squared plus sine squared? Theta. Just one. So my total mechanical energy is going to simply be half kx m squared at any given point. Because I'll have cosine squared blah plus sine squared same blah, and that is simply 1. Okay, now Wednesday is Eid holiday, so we have two options. I can either continue, we have still 15 more minutes in the lecture. I can either continue or we can stop here and I can post a video for the rest of the material. Which one would you prefer? Okay. So your book has this section on torsion pendulum, which we are not going to do. Okay. It's interesting, but since we're running out of time, I'm not going to go through it. But we do have simple pendulums, which you have done in the lab. Okay. Now, before we go into the equation of pendulums, we'll talk about something called the small angle approximation. Okay. Now, if we have a small angle, very, very small theta, okay, which is less than 1 radian, okay, or which is less than 1, okay, we can use the approximation that sine theta is approximately equal to theta. Okay, you might have used this in geometry before. Sine theta is approximately equal to theta. The question is, how small is small enough? Let's try it out. Say I have 5 degrees. My theta in radians is going to be 0.087, and my sine theta is 0.087. So far, so good. Let's increase it to 10 degrees. My theta is 0.174. My sine theta is still 0.174 to 3 decimal places. This looks really good. 15 degrees. My theta is 0.262 radians, and my sine theta is 0.259, which is only 1% off, which is really, really good. If I go to 20%, to 20 degrees, we end up at 2% errors. So if we keep theta under 10 degrees, then we make less than 1% error. If, however, we go up to 15 degrees, we only do 1% error, which is still not too bad. Above that, we usually don't want to go. Yeah, then we actually use sine theta properly. But up until this 15 degrees mark, or 10 degrees mark, sine theta is approximately equal to theta. Which means if I look at this pendulum, which is going left and right, and I look at its forces, I have Fg down. I have Fg sine theta and Fg cosine theta. Now, this thing is going like this and then back like this. So there is rotation. What is my torque? Torque is R cross F. My R here is going to be my length of the rope, L. And my F is going to be Fg sine theta. So minus L Fg sine theta is equal to I alpha, which gives me alpha equals minus mgl over I multiplied by theta. In simple harmonic motion, we know A is equal to minus omega squared x. And that means I can actually, express omega as square root mgl over I. T is equal to 2, omega is equal to 2 pi over t. So my time period will end up being, once I take all the, mess out, 2 pi square root L over G. What is interesting about this equation? There is length, there is gravitational acceleration G, but there is no M. There's no mass in that equation. So what this equation is telling us, that within the small angle approximation, it doesn't matter whether my pendulum has, a piece of M&Ms at the end of it, or it has an entire human being or a rocket at the end of it, it will still have the same time period. Which is weird, if you ask me. So if I have a kid swinging on a swing with some period t, and a second kid climbs on with the first, doubling the weight on the swing, what will the period of the swing be? Now, the answer might not be as obvious as we usually expect. Now, what would we expect? We would expect, since there's a heavier person, the time period would change, right? But here's the thing. What did our equation tell us? It told us that the time period is equal to 2 pi square root L over G. Where is mass? There is no mass in that equation. Since there is no mass in that equation, that means there's no change. Whether you have 1 person or 10 people on that swing, it would still go with the exact same time period. No one told us this when we were children. We kept trying to go harder and harder. A pendulum clock is adjusted at sea level. The clock is then taken to an altitude of several kilometers. How will the clock behave in its new location? Again, T is equal to 2 pi square root L over G. Now, if I go to a higher location, what happens to G? As we know, G depends on your distance from the surface of Earth. So the higher up you go, from our chapter on free fall, the higher up you go, the lower your G value. The lower your G value, the bigger your right-hand side of equation is. So you end up with a bigger T. A bigger T means that your clock will actually not give you the correct time, because the clock will run slow. It will take 1.x seconds to just go one proper second. So in a physical pendulum, something like this that is rotating, for small angular motion, the period is given by t equals 2 pi square root I over mgh. And I'm not going to derive that, you can just use it. Okay, so that is that. That's that, actually. We are done with this course. So if you have any questions, I'm happy to take them. Otherwise, that's it, we're done.
Thank you, Doctor.
Okay. I hope it was an interesting course. We had ups, we had downs. We had some good lectures, we had some boring lectures. We went quite fast in today's lecture because we're running out of time. But I'm hoping that, by the end of this course, you have learned some new things, you had some fun, and that if at the very least, you're a tiny bit more interested in how the world works now than you were when you started this course. I look forward to seeing you in the exam next week, inshallah. And yeah, best of luck.
Doctor.
Yeah?
In the beginning of the class, we were